Hello and welcome. I'm your host Shakil Khan. In this presentation today, I will show you the physical implementation details of my AC phase control system, as how all these subsystems interact and how all this comes together. So the AC phase control system consists of three subsystems. A zero voltage crossing system, which is to detect the zero voltage points in the line voltage, and a QUADRAC driver, which is to drive the AC load using a triac-diac combination from the microcontroller, and third, the microcontroller itself over here. Let's get started and talk about the zero voltage crossing detector. What you see here is a transformer, and here is the line voltage coming in. I live in Canada, so we have 120 volts for voltage, and it's delivered at 60 Hertz. This transformer steps the voltage down to 28 volts AC, and I use a resistor network or a voltage divider to reduce this voltage to 4.1 volts. The reduced voltage is now fed to an operational amplifier. It's here, and through a current limiting resistor, this goes to the inverting input. The non-inverting input is grounded, and I also have two clamping diodes between the inverting and the non-inverting inputs. Their function is to clamp the voltage levels to plus 0.7 volts or minus 0.7 volts. That's to prevent excessive voltage is happening at the input and to prevent any damage to the operational amplifiers. So when the voltage exceeds 0 volts, the op-amp output will saturate to 5.2 volts, or when it's 0 or below 0, it will remain at 0 volts. And that's how I get a square wave, and that's a way of detecting when the zero crossings are happening. Now I'll turn the oscilloscope on and I'll show you how this works. Here are the waveforms. What you see at the top is the input going to the operational amplifier, and here is the output. I have placed cursors. This horizontal cursor here is the zero voltage point for the AC wave, and the vertical cursor where it intersects. As you can see, when there is a negative on the negative cycle, we do not have a pulse, and when we have positive, for the positive part of the AC wave, we have a pulse. The GPIO port, or the general purpose input IO port of Raspberry Pi controller, can be programmed to detect a rising edge or a falling edge of a pulse, and that's the technique I'm using to know where the zeros are happening. Next, we'll talk about the other two subsystems, which is the QUADRAC driver and the microcontroller and the Raspberry Pi controller itself. Next, we are going to talk about the other two subsystems, which is QUADRAC driver over here and Raspberry Pi controller over here. I have the Raspberry Pi controller connected to my home network. The advantage of that is then I can use a remote desktop session on my laptop to connect to it. Okay, let's go through the details of the QUADRAC driver. I built this system using a commercially available AC dimmer switch. It's a simple circuit. It consists of 4 components: an inductor, 2 capacitors, and a variable resistor. And the QUADRAC device is over here. The inductor and one of the capacitors is to suppress noise, because as this device goes into conduction and out of conduction, it happens so frequently that can generate some electrical noise. The other capacitor and the variable resistor, that's a RC system. It's for timing. It's to determine the conduction angle. I've made one modification. So I'm not using this RC system for controlling the conduction angle, which requires manual control. So you have to use this, you have to change the resistance manually. Instead, I'm taking it to the Raspberry Pi controller. However, there is one catch. I don't take this directly to the Raspberry Pi controller. Instead, I'm using some optical isolation. And the reason for that, for doing this, is safety, because I want to have the high and the low voltage sides separated. On the optocoupler, this is the input side and that's the output side. I have the control signal coming from Raspberry Pi here. It delivers 3.2 volts. However, the 3010 optocoupler chip can take 3.2 volts, so I had to reduce the voltage using a voltage divider. So 1.2 volts goes into the input, and when it receives that voltage, the output goes into conduction, and then that triggers the diac, and as a result, the triac gate gets triggered and the current starts flowing to the AC load. I'll give you a demo of this in a little while, but let's keep going and also talk about the Raspberry Pi controller. So here is the Raspberry Pi controller board. What you see here is these are the GPIO, or the general purpose input output ports. I'm using 3 of the ports. One is for detecting the zero voltage crossings of the AC signal, and the other pin is for controlling the QUADRAC, and the third pin, I'm using it for temperature sensing, which is this one here, this tiny device. This is a Dallas 18B20 programmable resolution single wire digital thermometer. I was surprised to see how much this device can do. The tiny device can do an analog measurement, and it can convert everything to a digital stream that you can take and directly connect it to your to the GPIO port. Okay, so that's the Raspberry Pi controller. Next, I'm going to give you a demo of how all this comes together. I have my oscilloscope over there, and the laptop running a Python script to control do the controls for this AC load. I have 2 versions of this Python script. One will introduce a delay of 3 milliseconds after detecting the zero voltage crossing, and we'll see how that affects the waveform and the brightness of the light bulb. And then I will introduce a 6 millisecond delay, and then we'll see how that affects the waveforms and the brightness of the light. Actually, I'm in reverse order. We'll do the 6 milliseconds first. Okay, so I'm going to turn this light off and we'll zoom in. Okay. As you can see, this is what a full waveform looks like, and this is what a clip one looks like. I'm going to stop this so that you can see it clearly. Okay, I put two cursors here so that you can see after the zero voltage crossing, and we're introducing some delay, and yeah, you can see there is some delay here, and then it conducts for this tiny amount of time, and then it's turned off again, and it conducts for a little while on the negative cycle. And you can see the intensity of the light bulb. It's looking quite weak. It's not very bright. Okay. Now I'm going to introduce a delay of only 3 milliseconds. That's half of 6 milliseconds, and we'll see how the waveform and the intensity of the light changes. As you can see, now it's conducting for a longer duration, and that also reflects in the intensity of the light intensity. It's much more brighter now. So this is how the phase control works. This is how you can limit the power going to a AC load. I hope you have enjoyed this presentation. Thank you for watching it.